All right, everyone. I would like to go ahead and introduce Peter Grant, who is our next presenter. Let me pull up my notes. Apologies. Peter Grant has over a decade of experience performing public interest water heating research, evaluating the impacts of new technologies and developing smart controls for buildings. His areas of expertise include developing detailed simulation models representing novel technologies, developing automated controls that optimize performance in response to the specific needs of buildings, and focus on user friendliness and success through the design and deployment. By the way, he's also a senior scientific engineering associate at Lawrence Berkeley National Labs. Welcome, Peter.
An introduction myself.
For your time today.
Sorry, what was that?
Just welcoming you and thanking you for your time today.
Oh, okay. Yeah. So great. Yeah, thank you. I was going to start this slide off with an introduction, but after Robert's great one, I don't think I'll bother. So today I will be telling you about a few different directions with water heating research that Berkeley Lab is currently pursuing. We're really trying to, as this title indicates, make water heating both more flexible in terms of when it consumes electricity and make heat pump water heaters more retrofit ready, meaning that it's easier to replace a gas water heater with a heat pump water heater. And I'll give you a lot more detail about that in the coming slides. Okay, that's not advancing. There we go. So some high-level background before we dive into the details is that we're really trying to solve two separate problems simultaneously. And the first is that as the Biden administration's goals really reinforce and push us towards, we need to decarbonize. And the Biden administration has set the goal of 50 to 52% CO2 reductions by 2030. That's only 7 years away, and net zero by 2050. Now, in order to achieve these ambitious goals, we absolutely need to decarbonize our buildings. We need to replace, gas stoves, gas water heaters, and gas furnaces with heat pumps in every building where we can possibly pull it off. We also have the simultaneous problem of the duck curve. At least it's well known out here in California. And this plot shows data from the International Energy Administration showing the demand in a typical day in California from 2014 to 2019. And you can see with each year that passes, as we add more solar power, the demand curve, roughly 9 a.m. to 4 p.m. keeps getting lower and lower and lower. As solar power is providing those needs, we don't need as much electricity from the grid. Meanwhile, if you advance to 7 p.m., you can really see that that peak demand is not decreasing at all because solar power isn't really providing much electricity at that time of day. And so we're exacerbating this curve every day. As we add more solar power, that midday net load decreases. And as we electrify buildings to meet the decarbonization goals, we're going to see more water heaters and more cooktops consuming electricity in that peak period. So the peak is actually going to go up. Now in 2019, that caused a 16 gigawatt ramp in the load that utilities need to provide over 4 hours, which is very hard for them to manage. And as we decarbonize and as we add more solar power, this is only going to get steeper and harder for them to manage. So we need to simultaneously address that problem while decarbonizing. As it turns out, the heat pump water heater is a fantastic technology that can really address both of those problems. As a high-level overview, for those who don't know, a heat pump water heater is a storage tank-based water heater. So it's similar to the water heater you probably have. It's this big cylinder sitting there somewhere. It has a storage tank that holds somewhere between 50 and 80 gallons of water in it. It's trying to ensure that that water is hot and ready for you to use at all times. And its primary heating source is the heat pump. So when the water in the bottom of the tank gets cold, it activates the heat pump, it reheats the water, and it makes sure it's ready for you to use. Now, there are some fantastic benefits to this technology. Prior studies from ACEEE and National Resources Defense Council have estimated that nationwide, replacing a gas water heater with a heat pump water heater reduces CO2 emissions by 58%. And in California, it reduces CO2 emissions by 73%. And this is just a result of the types of electricity production in the different states. And so as all of the states add more renewable power, those CO2 reduction numbers, both nationwide and in California, will continue to increase. So fantastic decarbonization technology. Then from the point of view of load shifting, they already have all the capabilities that are necessary. Since they have this large storage tank, energy storage is a core component of how they function, and we can change the time of day when the water heater consumes electricity without impacting the hot water delivered to the occupants at all. So people may not even know this is happening. It's just doing what needs to be done. They also currently have CTA 2045 and Web API communication capabilities, which enables us to send all of the signals that are necessary to change the time of day when it consumes electricity and shift electricity consumption from that evening peak to that midday trough. They're kind of ready to go. But as always, there is additional research that can really help increase market penetration of both heat pump water heaters and load shifting technology. And so I'll be telling you about two things that we're pursuing to help achieve those goals. The first is what's called a retrofit-ready heat pump water heater. And retrofit-ready really means that it uses a 120-volt electric circuit instead of a 240-volt electric circuit. And both Department of Energy, Berkeley Lab, and several other organizations believe that these products will really enable using heat pump water heaters in cases where you are replacing an existing gas water heater just by reducing the cost. So as you can see in the picture on the left, which shows a typical natural gas water heater, there's no electric power on this product. It is not plugged into any sort of electrical socket because it just doesn't need it. Whereas a traditional heat pump water heater requires 240 volt and 30 amp electrical service, which is a really specialized connection, right? Many homes, the dryers may have that connection, the clothes dryers, but that's probably the only one, which means there really isn't the connection that you need at the gas water heater. So if you want to replace a gas water heater with a traditional heat pump water heater, you typically either need to find a 120 volt circuit that's nearby and upgrade it, or have an electrician add a completely new circuit, and this is going to run $2,000 to $4,000. Now, if somebody's replacing a water heater and their choice is a $500 gas storage tank, or the price of a heat pump water heater plus $2,000 to $4,000 to upgrade the electrical service, I don't think I have to explain to anybody that that's not appealing. It's just very expensive, and so it doesn't happen very often. Now, these retrofit-ready heat pump water heaters are specifically designed to use a 120 volt 15 amp circuit instead of the 240/30. And while the gas water heater doesn't, or historically hasn't required that, a 120 volt 15 amp circuit is, it's just a standard plug. And these are very common in houses. So even if one was not provided at the water heater because the water heater needed it, there's going to be one within 10 to 15 feet just because they're so common. And this enables you to take out that gas water heater, put in the heat pump water heater, plug it into an outlet that's close by. You can avoid the $2,000 to $4,000 electrical service upgrade charge, and hopefully we can really drive higher market adoption by reducing the installation costs. Now, there are still some technical challenges to overcome that may impact market adoption of these technologies, right? I tend to say that heat pump water heaters have traditionally been 240 volt 30 amp for a reason. And that reason is just that you can heat water more quickly if you have 4 times as much electricity available to do it. If we compare the 40-gallon gas water heater to the retrofit-ready heat pump water heater, on 2 specs, the first being the first hour rating and the second being the recovery, we can see for the 40-gallon gas water heater is 84 gallons, and for the retrofit-ready heat pump water heater, it's 45 gallons. So what this means is that assume you start with a hot tank of water, you turn on the shower, and you just use it until you get cold water coming out of the shower, and then let it reheat and start doing it again. In 1 hour, the 40-gallon gas water heater can give you 84 gallons of satisfactorily hot water, whereas the retrofit-ready heat pump water heater is down at 45, so about half. Then if you completely drain the tank, the 40-gallon gas water heater's recovery time, or time to bring the cold water back up to the set temperature, is 45 minutes, whereas the retrofit-ready heat pump water heater is almost 4 hours. Now, I personally think these specs for the retrofit-ready heat pump water heater are good enough, right? 45 gallons of first hour rating means you can, in California, spend about 45 minutes in the shower before somebody gets cold water. And that's showers for 4, maybe 5 people in some houses. Then after we take those showers, we go off to the office. We're not even home for 8 hours. So if it takes 4 hours to recharge the tank and the tank's recharged around noon, that's fine too, because we're not even there. But the market might disagree with me on those points. So the Department of Energy and manufacturers and Berkeley Lab really want to look into ways we can change the design of retrofit-ready heat pump water heaters to improve the first hour rating and improve the recovery time, so that when people are replacing their water heater, they So we are talking to DOE about pursuing a project where we look with the first hour rating and the recovery time. The first thing we'll look at is increasing the heat pump size. These heat pump water heaters typically use about 400 watts, whereas the code limit for a single device, which a ready heat pump water heater is likely to be, is 900 watts. So we can double the size of the heat pump and still have it meet code requirements. We also are looking into changing the design from this wraparound coil at the bottom of the tank that slowly heats the bottom half of the water to a single pass heat pump, where you pull cold water from the bottom of the tank, bring it to the heat pump, heat it to the set temperature, and put it back into the top of the tank. In this way, we would increase efficiency of the product, and it would also contribute to the first hour rating, whereas the current design takes so long to reheat the water that the first hour rating test is done by the time it's able to prepare hot water. We can also look at increasing the set temperature of the water heater. So these products typically include a mixing valve, so you can make the temperature of water in the tank whatever you want, typically increasing it so there's more energy stored. And then it passes through this mixing valve that combines the hot water from the tank with cold water to send out a consistent temperature to the occupants, about 120 degrees Fahrenheit. If we increase the temperature of water in the tank, we increase the energy stored, and we increase the first hour rating. So some of these products currently use a set temperature of 140 degrees, but the refrigerant and the heat pump could go as high as 150 degrees, and so we can get more stored energy that way. We also intend to look into changing the refrigerant from R134A to propane, and that's primarily because propane has a much lower global warming potential. So as refrigerant leaks out of the heat pump, it has a much lower impact on climate change. Now, if we make these changes, the table at the bottom shows how that impacts the first hour rating and recovery time. And I should highlight these are my back of the envelope calculations. So these changes would improve the first hour almost 4 hours to a little under 2 hours, while also providing more energy. So this could significantly improve how the market perceives these products. We can also look at redesigning the tank, with the primary change here being replacing the insulation that heat pump water heaters use with a higher quality insulation. In that way, we can get the same total insulation with a smaller amount of insulation, or we get the same insulation value with a smaller volume of insulation, which would allow us to increase the size of the storage tank inside the product. And since there's a larger storage tank, there's more energy stored, you get a better first hour rating. So if we combine the heat pump redesign with this insulation change, we get up to a combined first hour rating of about 82 gallons, which is awfully similar to that 84 gallons from the gas storage tank water heater. And so we're proposing, collaborating with researchers to make all of these changes and really try to make these products something that the market chases. One other problem that we intend to look into is the cost implications of installing these specifically in multifamily buildings. Now, heat pumps really move heat from one fluid to another. So in the case of the heat pump water heater, they extract heat from the air surrounding the water heater and put it into the water. As it extracts heat from the air, it makes the surrounding air colder, which reduces the performance of the heat pump, and in some cases can even make the surrounding air so cold that it is not safe to operate the heat pump, and you risk damaging it and destroying the product. So research has shown that in order to avoid these problems, a heat pump water heater for a single family building must be installed in a room that's about 450 square feet and empty. So that's basically saying you have a garage with only a water heater in it. Now, in most multifamily buildings, and just for reference, this picture is my closet of my water heater in my condo. And in most water heaters, those closets are less than 200 square feet. In mine, the closet is about 50 square feet. So in these cases, manufacturers say you really need to install 8-inch diameter ducting, pulling air from outside the building, putting it into the heat pump, and then directing the exhaust air back outside the building to avoid, really cooling off the little closet and causing those problems. This adds installation labor cost. In the case of condos, you have to get approval from the HOA, which is a major headache. So this is really going to mitigate how many people adopt these products. We are pursuing a project where we really try to leverage existing resources instead of using that 8-inch diameter duct. So if you're replacing a gas water heater, there's going to be a 4-inch diameter gas flue. Maybe we can redesign the heat pump to use that. Or in my case, there's a dryer right next to the water heater, which has a 4-inch diameter exhaust. Maybe we can redesign the heat pump to use that. And so these are all the things that we intend to look into. The other technology that I want to talk about is price responsive controls. And this is really aiming to help stabilize the utility grid while reducing people's utility bills. Coming back to our high level goals and the duct curve, really what we're trying to do is make heat pump water heaters consume less electricity during that peak period and shift that load over to the midday solar period. Now, this is not something people have really done historically because there was no reason for people to do it historically. That plot right there shows a historic electricity price in Pacific Gas and Electric Company territory. And you can see it's flat. It does not change throughout the day. So if you change the time when you consume electricity, you don't get any sort of discount on the electricity itself. Meanwhile, if you shift load, that inherently makes the product less efficient. So you're consuming more kilowatt hours, which basically means load shifting historically was increasing your own utility bill to do a favor to Pacific Gas and Electric Company. Not a very good sales pitch. But that's why we now have time of use rates. So this is an example of a current PG&E time of use rate. And now there's a high price from 4 p.m. to 9 p.m. And anything you can do to avoid consuming electricity from 4 p.m. to 9 p.m. by shifting it to earlier times of day means you pay fewer dollars per kilowatt hour. And there's now a financial incentive, a way for you to reduce your utility bills by helping out PG&E. Berkeley Labs CalFlexHub project is really taking that one step further. And we're proposing that we can get better load shifting results by, instead of using time of use rates, using highly dynamic prices. And these prices are intended to represent the cost of actually operating the utility grid. So at times of day when there's so much solar power that we actually have a problem managing it, the price of electricity will be very low. And at other times when the grid is really stressed and the utilities are asking us to reduce load to avoid overwhelming the grid, the price of electricity will be really high. And these prices will be based on 24-hour forecasts. So you can get a price curve similar to this one sent to your device, which then can predict the best way to operate your device and give you the best economic incentive to shift load away from a high price period to a low price period. And like I was said there, the CalFlex Hub architecture is to send prices to devices, and then each device will have an onboard controller that minimizes the operating cost. Now, let's look at the current status quo with heat pump water heaters. If you send a highly dynamic price schedule to a heat pump water heater, it will do nothing differently, precisely nothing, because these products do not know how to respond to price schedules. We simply haven't developed those controls yet, which is where Berkeley Labs research comes into play. We are currently developing a controller that explores these price structures as they come in, and it's looking to identify significant price changes in the coming hours. If it sees that the price is going to decrease, as happens between 7 p.m. and midnight on this plot, or between 6 a.m. and 9 a.m., then it will delay consuming electricity and operating the heat pump until a little bit later, so that it can consume less expensive electricity for that heating operation. Similarly, if it sees that the price is going to increase, it will start heating earlier to consume electricity when it's cheaper, rather than waiting until electricity is more expensive later. And after it makes sense of this price curve, it develops a schedule of CTA 2045 control signals that really minimize the operating cost of that heat pump water heater. And since heat pump water heaters are now required to have CTA 2045 capabilities, a grid operator would be able to, collect this schedule from Berkeley Lab and send signals out to heat pump water heaters in the field, signals similar to this schedule here that I have on the slide. So the deployment architecture we have in mind is similar to this, where it really starts with the price server. It's currently the CalFlex Hub price server, but in the future, this could be the PG&E price server, the Southern California Edison price server, SMUD, or nationwide, it could be, say, Xcel Energy. And these price servers send price signals to the cloud control server, which would host this control logic. It would also have knowledge of the different heat pumps or heat pump water heaters that are out in the field, how they typically consume electricity, how the occupants are typically behaving. And so it's able to generate a control schedule that's customized to these different price schedules and these different occupant behavior patterns. It then sends these price schedules to different program implementers, which may be a consultant working on behalf of the utility like Olivine or Skycentrix, or it could be the utility themselves. And then these program implementers take those control signals and send them out to the actual heat pump water heaters so that they get the signals, they shift their load, they do what the grid needs, and they save people money. So I have a couple of sample results here showing about how that's working in simulation form. And this shows an example of response to a highly dynamic price schedule. The plot on the top shows the price of electricity in dollars per kilowatt hour, and it's a little crunched, so you can't make out the specific numbers very well, but you can see the trends. It starts, average price at midnight, then it gets a little higher at 6 a.m., very low during the midday period, and very high in the evening peak period before tapering down again. The plot on the bottom shows two different load curves. One is using the manufacturer's control logic, that's the blue dashed line, and the green solid line shows the load curve if these heat pump water heaters are using Berkeley Labs control signals and the CTA 2045 schedules. Then the red highlight shows times of day when the price of electricity is above the average. And this is looking at 148 different heat pump water heaters, all in a fleet. And we are developing different strategies, different CTA 2045 control strategies, depending on the typical load of the heat pump water heaters. So there is some customization in response to how people behave. And as you can see, it's doing exactly what we want. It's increasing consumption of electricity between 9 a.m. and 4 p.m. So it's increasing that load, that low load during the midday period. and it's using that to pre-charge the tank. So the water in the tank at 4 p.m. is now hotter than it would have been without these controls. So it's ready to go into the high price period in the evening without consuming any electricity or consuming less electricity and still meeting the hot water demands of the occupants. In this way, it's both reducing the utility bills of the occupants and helping to stabilize the grid. The impacts of this day of simulation are really that we achieve a 29% cost savings for the people paying the utility bills, while reducing the total consumption during those high price periods by 75%. And we're increasing the consumption during that midday solar peak period by 102%. So we're very pleased with this, and we're looking forward to transferring it out of simulation to the lab and field monitoring, and advancing on that pathway to widespread deployment. But one concern that I can envision people having with this is that our solution is done here using highly dynamic prices, using research prices. What happens if we use actual price schedules that people are paying every day? Well, here's a similar result showing what happens if we use Southern California Edison's time of use D 5 to 8 p.m. schedule. And it really shows the same thing, but with a different curve responding to a different price schedule. And in this case, the utility bills are reduced by 15%. So not the same 29, not as much, but still saving people money. We're reducing electricity consumption during that 5 to 8 p.m. window by 77%. And we're increasing midday consumption by 63%. So not as dramatic, but still doing everything we need it to do. Okay, and so that talks about, or that's the price sensitive or price responsive controls we're developing. And so just a few key takeaways that I had here is that Berkeley Lab, supported by DOE and working with manufacturers, is really working on ongoing research and development on heat pump water heaters to help achieve these decarbonization goals. Heat pump water heaters already have all of the necessary capabilities, right? They're very efficient. They're electric, so they're great for decarbonizing. They have communication capabilities so that we can implement controls that shift load. They have everything we need. These retrofit-ready heat pump water heaters are already entering the market, and I personally believe that they will meet almost everybody's needs here in California, but we're still working to improve their performance, just for those people who disagree with me there. And we've also developed price responsive controls that can drive the needed load shifting to enable consuming excess solar power and reducing peak period consumption, all while reducing utility bills for program participants. Thank you. Do we have any questions?
Peter, we do have a couple of questions. First off, thank you very much. That was an amazing presentation. We have very little time for questions, so I'm going to prioritize two that I think are really appropriate. First, Christian asks, do you look at expected water demand when you use price responsive controls? You wouldn't want to delay heating up water just before morning showers, for example.
Yeah, that's a very good question, Christian. And so 2 comments there. One is that when I say we're simulating 148 heat pump water heaters, that really means we have the same heat pump water heater in 148 different houses. And each of these houses is using a different, has different occupant behavior patterns. So they're consuming different amounts of hot water at different times of day, right? Maybe one person takes a 10-minute shower at 8, another takes a 5-minute shower at 9, these kinds of differences. So that's point 1. Point 2 is that these heat pump water heaters do still have the onboard, the manufacturer's control logic installed. And so anytime there's a risk of running out of hot water, maybe that's less common with our controls, maybe more common, but anytime that risk arises, the controller activates the resistance elements to make sure there's hot water. So we are not reducing how well people get hot water. That onboard controller is still responding accordingly.
Fantastic. Thank you, Peter. And our last question from Robin, you showed that the increase in first hour performance being almost doubled by insulation. This implies that over almost half of the heat being added by the heat pump is lost. That seems a little high.
Okay. So I think maybe I went through this too quickly and there's a bit of a misunderstanding. I assume, Robin, you're talking about this change from a first hour rating of 45 to a combined first hour rating of 82. And that combined here is really combined status quo to better insulation, plus all of these changes. So I'm basically saying you can go from 62 first hour rating to 82 by using less high quality insulation and therefore a larger storage tank.
Fantastic. So it's a combination of all the technologies, and we're not really increasing the amount of insulation. We're increasing the size of the tank as a result of using better insulation.
Yes, that's a great way to describe it. And my apologies for flying through that too quickly.
Not at all. All these presentations are so fantastic. All our presenters are fantastic, and our attendees are just top notch and ask some amazing questions. So
I'm noticing that.
I apologize to everyone
good.
whose questions we didn't get to, because we are out of time before we move to our group panel sessions. So thank you again very much, Peter. And thank you, everyone. We will see you in the group sessions.
Okay. Thank you for having me, and have a good one, everybody.
Thank you again, Peter. That really was fantastic.
Yeah. You're very welcome, and thank you. Oh.